So we've finished today's afternoon. We are going to use the board. Let me use the race. And then erase. With Tom Stoiber. Tom is working now at Yeshiva University with the Hamiltonians group. He finished his PhD in mathematics, if I'm not mistaken, in Erlangen. And he's going to tell us about violations, correspondence, topological insulators. Tom, thank you very much.
Okay. So, thank you. And this is Johannes Kellendonk from the University of Lyon, and who is also very prominent person in mathematical theory of topological insulators and like edge correspondence. Okay, so first of all, I need to give a quick rundown of what we mean by bulk edge correspondence in our context. And I think we started a definition of topological insulator, which everybody here should roughly know. So, I mean, you can define it in subtly different ways, but generally a topological insulator should be an insulating material that in some sense cannot be deformed to some trivial insulator called passing through some intermediate conducting state. And usually we think of these guys in parameter space, where they are just given in the form of gap Hamiltonians, where the projections, I mean, we are thinking in the non-interacting picture, spectral projections, which have some topological variance, and therefore, if we have some homotopy, those topological variants stay the same unless we close one or more of the gaps. So the phase boundaries are exactly the point where the gaps close. In a parameter space, we can also think of these guys in real space. And then we have materials which are insulating in the bulk, but if we make an interface with some other material, particularly with a trivial insulator, then there can be conducting edge modes which are protected by their own topological variants. So in particular, an interface with empty space or with air, it's just the boundary of the system, which was edge mode. Now in principle and in practice, those two are not the same, those do not give the same classification, mostly because they can be more invariant if we classify parameter space. So spectral projections can have topological invariants which do not lead to edge states or only lead to edge states for certain boundaries, like the speed topological invariance. But what we should have in general is like bulk edge correspondence principle, which is not an exact duality, but it tells us that the bulk invariance exactly determine the edge invariance. So what this means is that the classification in parameter space is in some sense more fundamental, which is great for us because usually classifying gap Hamiltonians is easier than classifying all possible boundary states for all possible boundaries. That's why this principle is so important. And let's make this very concrete. So the only example that I really want to look and discuss is the complex A class in 2 dimensions, so the integer quantum Hall effect. And so what we're looking at here is some kind of half space band structure. So we have some 2-dimensional lattice, we cut it in half. And we are only looking at one half space, but it is infinite. So and then the specs, we still have one periodic direction, so we can Fourier transform in this parallel direction and look how, so basically our Hamiltonian is a family of 1-dimensional Hamiltonians, and we track how the spectrum depends on momentum. And what we get is a lot of, so this entire solid black is the spectrum of the bulk. So this is so it is gapped. And in addition to the bulk spectrum, we get isolated eigenvalues at the boundary. So these are edge modes. And we can be quantitative here, and we can count the number of edge mode bands that we get, and we count them with their chirality. So an edge band which goes from the top band to the bottom band, we count at -1, and one that goes in the other direction counts at +1. And the bulk edge correspondence principle just tells us in this case that the bulk chunk number of the bottom band should be the same as the edge conductivity inside the gap. So this is a formula which is ascribed to Hasselbeck, who discovered this in the relation in the 90s, but I'm not so sure he was really the first. And yeah, so this is basically, we have some edge topological invariant, which is also an integer, and this edge conductivity, I mean, it's an integer that is much more easily expressed in terms of this count of edge bands, which happens to be the same, happens to give the same size. And in mathematics, we simply call this the spectral flow of a family of self-adjoint operators. So we just count the number of edge eigenvalue bands which cross the gap. So this is what we expect, right? Now, a few years ago, a group of one mathematician, two physicists, Stoiber, Dallas, and Benai, found an apparent counterexample to this bulk edge principle. So what they were looking at was this Hamiltonian here, which is, you can see, is a differential operator. So this is what they call the shallow water model. So this is you could say it's a metamaterial Hamiltonian. So this differential operator describes some shallow water waves in a very particular model. It's not really important what this represents and how this is derived. But in any case, one can analyze this Hamiltonian with the same kinds of topological principles that it always does. So one can Fourier transform and look at the Chern number of the bulk band, and one finds that this guy has 3 spectral bands. So there's one band here, there's a one band here, and in the middle there's something weird. There's a flat band, so an infinitely degenerate eigenvalue at 0, which just comes from this off-diagonal structure. So this is basically a spin 1 particle. But in any case, the bottom band has a Chern number of -2. So what we expect is to have two edge bands which cross the gap. And so that's what they expected to find. And so they checked for a few boundary conditions and found that this does not really work out all the time. So for this boundary condition here, which is on the bottom, it actually works. So you have 2 bands of edge modes which cross the gap. But for these 2 boundary conditions which they have here, it doesn't. So I'm not even going to tell you which is which. It's just enough for you to know that it depends on what the boundary condition is, which is kind of a puzzle, because really we had some rigorous proofs of like edge correspondence before, like even for these continuous kinds of models. So it's a bit worrying if someone else comes up with a counterexample to one of the things that they thought are proven theorems. So together with Johannes, I mean, we have a bit of skin in the game. Johannes and my PhD advisor, Hermann Schulz-Waldes, were one of the first people who ever proved this bulk edge correspondence rigorously. Yeah, so we set out to find out what is going on in these models. Right.
So yeah. They have this odd viscosity term, but I didn't see it.
Yeah, this odd viscosity term is this guy here, this proportional to mu. So this you add this second order term, so you can okay, so you can discuss this more with this odd viscosity term or without it. It changes the structure of the Hamiltonian a lot, but the phenomenology is the same. It's that the number of edge modes depends on what the boundary condition is. Okay. So the problem is this Hamiltonian actually has many problems. So analytically, it's super ugly. I mean, it's not an elliptic operator. It has this flat band, and it's a mixed order PDE, which is bad. So you have 3 equations, but when you go to self-adjoint boundary conditions, you can actually only impose 2 conditions. So one of the vector components is unrestrained at the boundary, no matter what you do. So there are all sorts of things that could go wrong here with this model. So it's not clear what exactly causes the bulk edge correspondence to be violated. But luckily, they have an analytically much nicer example, which is the so-called regularized massive Dirac Hamiltonian, which is a model that is probably familiar to many physicists here. So you're just looking at a 2-dimensional massive Dirac Hamiltonian, and there you add some second order term, which gives it much nicer analytical properties. So this is basically a K.P model for 2 bands of a Chern insulator. And we are looking at this as a model on a half space, and we will later give it a self-adjoint boundary condition. first, the bulk spectrum is very simple, so we have basically two cones. They're separated by an energy gap, which is as large as the mass term, and we do get a bulk Chern number, which depends on the sign of this mass term and the sign of this regularization epsilon. Okay, so this is topologically non-trivial. And we put translation invariant boundary conditions, so we still have one remaining translation invariant direct in the system, so we can Fourier transform, which turns this Hamiltonian basically into a family of Hamiltonians, which depends on momentum. So we can still make surface band structures. But first, the first thing any reasonable person would do is to look at Dirichlet boundary conditions. So we just impose that both spinor components are zero at the boundary. And what one can see is basically everything checks out. So depending on what your bulk Chern number is, you get either one edge mode which shows the gap from above or from below, or you don't get any edge modes at all. That is exactly what we want to see. But now what these physicists also have as a counterexample, they have an additional boundary condition where you now impose for the second vector component that the first and second derivative in the x and y direction are proportional to each other by some imaginary factor alpha times r. And then what we see is that, okay, so I'm looking at this for parameter values where the bulk Chern number is -1, so I'm expecting one band of edge modes which shows the gap from above. But instead, I mean, this band exists, but it doesn't close the gap, it just walks off into the distance. Okay, this is for large alpha. For large negative alpha, we have the opposite problem. Now we have too many edge bands. Now we have two bands for some reason which close the gap. And then for alpha equal to 0, so which is in the middle, like edge correspondence works, but by now we have lost all confidence that this is not maybe just some freak accident of nature. So, what's going on here? So, I mean, as I said, we have proofs of bulk edge correspondence, but the problem is that people were a bit lazy or maybe negligent to not consider the problem of which boundary conditions you are actually allowed to put. So, in some sense, people probably were very optimistic and believed that actually you can put whatever you want. But, yeah. So, another problem is that this actually has zero to do with the bulk topology. You can play the same game with just the free Laplacian, which is topologically trivial by any account. We put similar boundary conditions where we relate the derivatives in the x and y direction. And you can see here's the same problem. If we vary this boundary condition, we get an edge mode which can go from -infinity to plus until it merges with the bulk band. So of course, for the physicists, this counterexample is maybe not so worrying because if your Hamiltonian is not bounded from below, you don't have to be afraid that you might accidentally encounter this in nature because it's not stable. But mathematically, it's still a valid counterexample. So, questions for this part? Okay. So, now I'm not going to make this a very mathematical talk, but I still want to give you a bit of an indication how we prove this bulk edge correspondence and what goes wrong in these continuous models. So what we're using is operator K theory. We are picking an operator algebraic approach where Hamiltonians which are affiliated to a certain C-star algebra. It doesn't really matter too much what these algebras are, but what this approach gives us is that we can classify our Hamiltonians by abelian groups, the K groups. So in the operator algebraic picture, we have this K0 group, which is generated by stable homotopy classes of matrix valued projections. And these projections should have entries which are in the unitization of a certain C-star algebra, which looks a bit complicated, but in essence, this comes about very natural application. So stable homotopy just means that we can make these matrices as large as we want to facilitate our homotopies. And then we also have this K1 group, which is defined by the same way, but instead of projection matrices, we take unitary matrices. And the way that this comes into play is, of course, that this K0 group will be used to classify spectral projections of Hamiltonians, which belong to particular algebras. And this K1 group takes the role of some kind of obstruction to gap opening. So this will be used to classify edge modes via some index theory. Okay, I mean, just take this for granted. So in the way that bulk edge correspondence works is that we have some algebra B, which describes our bulk observables, and we have some algebra E, which describes our edge observables. And there's many ways to construct natural homomorphisms, in some sense, which go from K0 group of B to the K1 group of E. For example, I mean, this comes mostly because K theory is a homology theory, so there are some natural boundary maps if you have an exact sequence of algebras, for example. And then the way this should relate to actual Hamiltonian is that this map should be such that it maps the class of the bulk family projection to some kind of K1 of E valued index of the half space. So what this means is that you have a gap in the bulk, but if you go to a half space, then this gap gets filled whenever this index is non-zero. So this is basically the topological invariant which classifies the edge modes causes the bulk gap to get filled. Okay, and this is in fact always true when we use unital C-star algebras. So for example, for discrete models on the torus, we can use as a bulk algebra just the continuous function on the torus. And then this is always true in the sense that we can just define this boundary map by this term. So every half space Hamiltonian has a K1 valued index, and it only depends on the bulk class. So this is basically true by definition. But if we go to unbounded Hamiltonians, things become more complicated, because the problem is now we have a non-compact momentum space, RD, for example, and we use non-unital C-star algebras to accommodate this. And this leads to a very fickle technical problem, which is that K theory is essentially a theory for finite degrees of freedom. So it's based on finite dimensional matrices over a unitization of the algebra. One must be particular and say it's a minimal unitization. If we have unbounded operators, then we accommodate this by replacing the unbounded operators by bounded operators. For example, we can make any unbounded divergent operator bounded by dividing by 1 plus the square of the operator, the square root of it. Basically, we normalize the spectrum to the interval of -1 to 1. The problem is this functional calculus does not land us in this unitization that we need. It lands us in the multiplier algebra, which is the maximal unitization. And for this very technical reason, this bulk edge correspondence can fail to correctly predict the edge mode. Now this took us a while to figure out. And the problem is in practice it means this bulk edge correspondence, which we thought is fairly universal, it only holds for very particular boundary conditions. And there's also often not really a good way to predict which boundary conditions we can use and which not. But there's some positive results at least. So let me give you a brief rundown. So let's make first a few definitions. So first, let's just talk about elliptic differential operators. So let's say a bulk Hamiltonian is elliptic if all the energy bands eventually tend to plus or minus infinity if we let momentum go to infinity. So I mean, this is what we expect to see anyhow. But these metamaterial kind of Hamiltonians can sometimes happen that they have a flat band. So this happens for the shallow water models, but also for example, if you take a Hamiltonian formulation of the Maxwell equations. I mean, this is basically because for spin 1 particles you can get this zero energy edge bulk band. Okay, so something like that we want to exclude, so we want to focus on this elliptic case. And similarly, we want to talk about elliptic boundary conditions. And For differential equations, elliptic is a very loaded term, so which can mean many different things. So, but for me, I would just say boundary conditions elliptic if the edge bands also go to plus or minus infinity in energy, or eventually merge with the Phi band. So something like this is okay, where the edge mode branch eventually, yeah, I mean, it doesn't really merge with the Phi band, but it's asymptotically meets it anyhow. So something like this is okay if you have something like an edge band which has a horizontal asymptote or something like that. That is not elliptic. So something like this causes problems in our topological analysis. But the nice thing is, if you just look at like translation invariant boundary conditions, which are involve only derivatives of a lower order than your Hamiltonian, then typically what you will see is something like this. So basically these kinds of edge mode branches which do not go to infinity in energy are a very rare event. Is what we have found. I mean, we don't really have a proof, but it looks like this is the generic case. And so then we have this positive result, which tells us that if we have a translation invariant second order differential operators are Hamiltonian, and we put directly on normal boundary conditions, then we can do bulk edge correspondence as we always did it. And the reason is simply that there are not so many of these Hamiltonians. Like we perfectly understand how differential calculus works with these guys. So the functional calculus works. So it's just basically n copies of the Laplacian with a positive sign and k times the Laplacian with a negative sign. So we can by hand check that this satisfies all the conditions that we need for bulk edge correspondence. This is maybe not so interesting, but what is also comforting is that in general, if we don't just use this special directly or normal boundary conditions, but just use any boundary conditions for which we have this elliptic property and for which the spectrum is also bounded from below, then we can also show that bulk edge correspondence works. Which is good, because in physics, of course, most of our realistic models are bounded from below. So we can, so this kind of, gives us the assurance that we usually won't get problems with the bulk edge correspondence. Okay, so these are nice positive results.
Can I ask a question?
Yeah.
So the Atiyah-Patoli-Seeger boundary conditions, I think they're non-local or something.
Yeah, they are non-local. There's a spectral boundary conditions. Yeah, we don't really know what to do with these. I mean, there are other problems with that. These are boundary conditions for Dirac operators, and they also for Dirac operators we already have problems defining the bulk invariant actually.
Okay.
But yeah, so this is mostly we're interested in local translation variant boundary conditions. Okay, so basically we have some few cases where we are sure the bulk edge correspondence works. Now our other problem was, can we somehow understand some other cases as well? So can we understand why in more detail bulk edge correspondence works? And we found an interesting topological invariant lurking somewhere around. So now we take a step back and become more abstract. So we're looking at some family of one-dimensional, formally self-adjoint differential operators. So which depends on a parameter. Formally self-adjoint means we need to pick some boundary condition to make it actually self-adjoint. And for local boundary conditions, these will always look like this. So for each value of momentum, we impose some matrix equation which involves the values of the wave function, the boundary, and relates them to the values of the derivative at the boundary, for example. And mathematically, it is well understood what one needs to, how these are classified. So the self-adjoint extensions are basically classified by so-called von Neumann unitaries. So those are unitary operators which map between the so-called deficiency subspaces of the operator. So for a symmetric operator, the adjoint is not the same as the operator itself. It can have a different spectrum M and a different domain. So therefore it can have an eigenspace for eigenvalues plus and minus I. And what we need to do to make this self-adjoint is to correct for this eigenvalue by adding some unitary operator. So essentially non-technical terms, you classify these boundary conditions by taking functions which take values in the unitary matrices of a certain degree. And then it can happen that we have two such boundary conditions or two such polynomial unitaries, and so those are unitary functions, so you may be able to compute a binding number of these two relative to each other. So you compute a binding number of one times the adjoint of the other. And if this binding number is non-zero, then it turns out that the spectral flows of the corresponding self-adjoint extensions differ in any bulk gap by exactly this binding number. So this means this corresponding self-adjoint extensions do have different number of edge bands in any gap. And we can classify this by this binding number, which abstractly classifies the boundary condition. I mean, it sounds strange, but it actually makes sense in sometimes that this happens. And there's a very concrete and practical example, which is also very familiar to physicists, which is so-called domain wall theorem. And so we have basically a two-dimensional Dirac operator. We give this a mass term which depends on space in one direction. So what we want to make is a domain wall which has like some mass on one side of the domain wall and some other mass on the other side. And we know that if this happens, if we have different masses asymptotically, then this domain wall binds some bound states, some interface states, and this causes a spectral flow, which is given by the difference of the signs of the mass, plus and minus infinity. Okay, so this is an interface model. It's not a half, but it's an interface. But we can now let this converge to an interface model by letting the mass go to infinity on one side of the boundary, one side of the domain wall. So it doesn't really matter how the details of this convergence work, but the point is one can do the analysis and one can actually prove that this Hamiltonian, that if you let the mass converge to infinity on one side, it converges actually to a half-space Dirac Hamiltonian, which has a very particular boundary condition. And namely, depending on which, if you let the mass converge to plus or minus infinity, it will get a boundary condition, which is either the so-called positive or the infinite mass boundary condition. A positive or negative infinite mass boundary condition. So basically, you relate the two spinor components at the boundary either with a plus or with a minus sign. So, and this convergence is actually the so-called norm resolvent signs, which are very strong topology, which tells us that the topological invariants are preserved. What this means is that whatever boundary condition this is, it must have the same number of edge states as our interface problem had. So we know that we also get two boundary conditions at least, which have a different number of edge nodes. And we can make this very simply by just drawing the phase diagram. So in the interface model, we have two parameters. We have the mass at positive infinity and with negative infinity. And depending on what this mass is, we get either 1 or minus 1 as the edge invariant. And on the half space, we can also be more general and take a boundary condition which just relates the first and second spinor component by some proportionality constant. And the phase diagram in both cases looks the same. And indeed, in some sense, they overlap because this line where this alpha is -1 or +1 is exactly the line where we have this positive or negative mass here. So what this means is, in some sense, we have some boundary condition here in the half space which remembers that we actually had some other Dirac Hamiltonian in the other half space which had some particular mass. So what this means is that some boundary conditions are not neutral in some sense. They encode non-trivial topological interfaces. So I mean, you could already criticize that these kinds of boundary conditions, these sharp boundary conditions, are not really physically reasonable. I mean, you could say it's just an abstraction. Usually, you have some kind of smooth domain wall, and for smooth domain walls, everything should work. But I mean, in principle, what this means is that these sharp boundary conditions can encode many different limiting cases of domain walls or interfaces. And therefore, one really needs to be careful when picking them. So not every boundary condition really corresponds to some kind of actual neutral boundary. So that's why sometimes it makes sense that the edge modes depend on what you choose as boundary condition. I mean, not always, but for special cases, we do understand it. Okay, so now we are almost done, but now there's one problem left, so which is that I've told you now that basically the number of edge modes more or less depends completely on what you choose as boundary condition. But then you might ask, what happened to the bike topology at all? I mean, where does it appear? And for that, we can go back to the regularized Dirac Hamiltonian, where we have this boundary condition which depends on some parameter alpha, and look at it in more detail. Namely, this time we can vary the mass term as well. So we have in this model two different phases, one which has Chern number of -1, and one which has Chern number of 0. And we look at the number of edge modes, so the spectral flow for various boundary conditions, including Dirichlet and all the various cases for this parameter alpha. And we find very quickly that there's a pattern in this table, which is that actually the second row is always larger than the first row by the same number, namely is larger by 1. And it's actually not an accident. This is it's simply the case that if we take these two models with positive and negative mass and put the same boundary condition, which is nice enough, so it should be elliptic, then this difference of edge invariance is always the same as the difference of the bulk invariance of these two models. And this concept is something that we call relative bulk edge correspondence. So this tells us that the bulk topology is not lost. We can still use the bulk invariance to predict edge mode, the occurrence of edge modes. It's just that the number of edge modes, so the relation between bulk and edge, can be shifted by some constant offset which depends on the boundary condition. And once we correct for that, we are fine. We can predict the number of edge modes. So technically what this means is if our Hamiltonian has the very common form that is some kinetic term plus some potential, then the boundary violation, so the offset from the usual bulk edge correspondence, depends only on whatever the kinetic term is. And then it's the same for all potentials that you use to open a gap. So basically all you need to do is classify all possible boundary conditions for the kinetic terms that you're interested in, and then you always know what you need to do to correct your bulk edge correspondence and to predict the correct number of edge modes. So this is very much a solvable problem. It's just a lot of work to do this classification. Yeah, okay, that's basically all I wanted to say. Is now I have conclusions. Basically, the short rundown is bulk edge correspondence does in fact depend on the choice of boundary conditions. But for second order elliptic operators, there's not so much that can go wrong, especially when they are bounded from below. Some boundary conditions we can associate topological charges, which lead to different numbers of edge modes compared to each other. And this is something which we can compute and understand. So we can also use these winding numbers to classify connected components of boundary conditions and to classify these. Some of these connected components of boundary conditions can also be, we can also compute differential X. So some of these connected components can also understand these charges or winding numbers by writing them as limiting cases of interfaces, where you have two non-topologically non-trivial materials. So those boundary conditions are actually abstractions of interfaces, not of real boundary conditions. And also one thing that I want to highlight is that these violations of bulk edge correspondence do not really just affect some isolated choices of boundary conditions. It's always entire connected components in the space of boundary conditions which have the same violation. So there's actually, once you have some violations, that affects always many boundary conditions. But we can, in some sense, classify these connected components of boundary conditions within K-theory. So this is also still ongoing work, and then once you have classified those violations, you can basically proceed as normal. You use this relative bulk edge correspondence to just, do your classification for translation invariant kinetic terms, and then you add whatever your bulk invariant is to that, and you get the final result for whatever, for the number of edge nodes. So technically, we have all the tools to correct bulk edge correspondence, just an enormous classification problem. Okay, so for the last slide, I just have some literature references. So, Thank you for your attention.